Okay, so we're going to learn first about the change of base identity, which is how you can evaluate logs with any base. One of the options, especially if you don't have the newer operating system on your calculator. So we're asked first to evaluate log base 5 of 25. What does that mean, Luhita? What does log base 5 of 25 mean? Exactly right. It means 5 to what power is 25? And what's the answer? 2. If you write it in exponential format, it would be 5 to the power x equals 25. That's what it would look like. So x equals 2. The answer to that is 2. Now, for part 2, it says evaluate log of 25 over log 5. Notice there is no base indicated there, which means those are common logs, and that means we can use our log button on our calculator. We just have to make sure that we close the bracket after the 25, so it only takes the log of 25, and then divide that by the log of 5. And you get the same answer. So what we see here is that log base 5 of 25 gives us the same answer as log 25 over log 5. Same answer. They both equal 2. So looking at part B, evaluate log base 3 of 243. So what does log base 3 of 243 really mean, Miriam? It means 3 to what power equals 243. And I think that is 4, I think. Let's just 5. Right, because 3 to the 4th would be 81. Yep, so this equals 5. And then if you evaluate log of 243 over log 3, so again, those are both common logs. There's no base indicated, which means it's base 10. So again, we can use the calculator to do that. Just have to make sure you close the bracket after log 243. And that also gives you the same answer of 5. So this tells us that log base 3 of 243 is equal to log of 243 over log of 3. So this tells us the change of base identity, right? Log base 5 of 25, is the same as log of 25 divided by log 5. Log base 3 of 243 is the same as log of 243 over log 3. So if we have log base A of B, that can be written as log B over log A. That's what it means. That is what's known as the change of base identity. And so write log base 2 of 64 in a form that can be evaluated using a calculator. That would be log of 64 over log of 2. Now that should equal 6 because log base 2 of 64 is really asking 2 to what power is 64? And that answer is 6. So this should also be 6. And we can confirm that on our calculator. And it is. So again, this is the change of base identity. It says that log base B of C is equal to log base A of C over log base A of B. Now, this is slightly different than what we wrote above in the box because in the box we didn't write a base. Normally, the reason you use change of base is so that you can write them with base 10 and use your calculator, which is what I did above. I didn't put a base there, which means it's base 10. So you can use your calculator. But in reality, you can use any base that you want as long as they are the same. And that's why both of these have base A in them. They can be any base you want as long as they are the same. Again, usually it'll be base 10. But you might be asked to express something with a base other than 10. Okay? So we can now evaluate log of base 4 of 1024 by going log of 1024 over log 4. Just got to make sure you close the bracket after the log of 1024. And so that gives us an answer of 5. Now, if you have the newer operating system on your calculator, you can also get it that way. Right? So if you go F2, I think, so alpha window, yes, number 5 in this list is log with a different base. So you can actually input it the same way that it's written, log base 4 of 1024. So if you have the newer operating system on your calculator, and again, to see if you do, go alpha window, and that gets you into that menu where you can choose number 5, which is log with a different base. Okay, so if you have that, you can use it. If not, you have to use the change of base identity. Now, part 2 says to evaluate that. So we're going to do some algebra here, right? Just so you can see that this will work as long as the bases are the same. When we did it for the first part, the bases were base 10, so we could use our calculator. But it doesn't matter what the bases are as long as they are the same. So here's how this works. Log base 2 of 1024 would be the log of 1024 divided by the log of 2. That's the top part, the numerator, if you use the change of base identity for that part. And that'll be divided by the denominator, which if we use a change of base identity would be log 4 over log 2. So we're dividing by a rational expression. We know that you can do that by multiplying by the reciprocal. So I'm going to do that. Instead of dividing by log 4 over log 2, I'm going to multiply by the reciprocal, which will be log 2 over log 4. And now you can see that the log 2's will cancel. And you're left with log of 1024 over log of 4. The same thing that we had over on the left. So again, this just shows you that as long as the bases are the same, like they are, those are both base 2, as long as they're the same, it'll work. Because those logs will cancel when you use the change of base identity. So now you can evaluate log base 5 of 221. This is going to be an irrational number, but you can get it from your calculator by going log of 221 over log of 5 using the change of base identity. That's one option. Again, you just have to make sure you close log of 221. Close the bracket divided by log of 5, excuse me. So to the nearest hundredth, that'll be approximately 3.35. And again, if you have the newer operating system, if you go alpha window and choose number 5, you can do it that way as well. Log base 5 of 221. Same value. So if you have the newer operating system, you can do it that way. So for part B, the log base 2 of 1 over 1,000 using the change of base identity, that would be the log of 1 over 1,000 all over the log of 2. So there's a log of 1 over 1,000, and that's now divided by the log of 2. Negative 9.96.97 would round to the nearest hundredth. So we've seen that you cannot take the log of a negative number, but sometimes when you take the log, you get a negative answer. That happens. We've seen that before. For question C, it's 3 times log base 7 of 512. So it'll be 3 times the log of 512 over the log of 7. That 3 is 3 over 1. So it's only the top that's multiplied by 3. So whether you use the change of base identity or the log function of your calculator, either way you'll get the same answer. So approximately 9.62. All right. So this one says to convert each of those to a base of 3. So this will be done using the change of base identity and making them both with a base of 3. It'll be log base 3 of 216 over log base 3 of 6. So whatever the base of the original log is, we should see that that is always in the denominator. It's the log of the argument divided by the log of the base. You're asked to write log of 300, which would be base 10, no base indicated, with a base of 5. So that would be log base 5 of 300 over log base 5 of 10. There's no base indicated for that log, which means it's base 10. So this next one wants us to find the exact value of the following. So we could use our calculator to check it, but we should also know how to do these without using the calculator. Like we did before, you'll let them equal x, and then you'll convert from logarithmic to exponential. So log base 3 of 1 over 729 means 3 to what power is 1 over 729. So we can do this by making the bases the same like we've done before. We just have to do some trial and error to see 3 to what power is 729. I think it's going to be 3 to the power 6. Yes, it is. So then we can say 3 to the x equals 3 to the negative 6. So our answer for x is negative 6. If we write both of them, both sides, as a power with the same base, then the exponents are equal as well. Okay, question B, let's work down below here just because we'll have more room. We want to know what 2 times log base 8 of 512 is. Well, first, log base 8 of 512. We want to know what that equals, so let's let it equal x. So that means 8 to the x equals 512. We figure out what x would be. And let's see if we can express 512 as a power of 8. 8 to the power of 3 is 512. So x equals 3. Huh? I'm going to bring it back in now. You have to keep the 2 separate from the log because it's not part of the log. It's 2 times that log. So I found that x equals 3, so now our answer will be 2 times 3. The 2 is a coefficient, it's not part of the log. So we bring it in after. Right? Question C. Negative log base 7 of 343. So in the same way, this is negative 1 times. And now to find out what log base 7 of 343 is, we'll set it equal to x. Sorry, it should be 1 over 343. So it's going to be negative 1 times. To evaluate that, we'll write it as an exponential function. And 343, let's see if that's 7 to the power 3. It is. So it's negative 1 times. So this will be 7 to the x equals 1 over 7 cubed. So negative 1 times 7 to the x equals 7 to the negative 3. So therefore x equals negative 3, and our answer will be negative 1 times negative 3. So the final answer for that one is positive 3. Question D. 5 to the power log base 5 of 25. What's the value of log base 5 of 25, Jinseo? Yes, because that's asking 5 to what power is 25. So that power is equivalent to 2, so the answer is 5 squared, which is 25. Part E says log base 2 of the root of 1 over 1024. So we want to find out what that equals, so let it equal x, and then we convert to exponential. It'll be 2 to the x. So I'll start to do some work with that radical expression by first, instead of saying it's the square root of that, I'll say it's to the power half. Because the left side has a base of 2, I want to get a base of 2 on the right side as well. And I think 2 to the power 10 is 1024. Yes, it is. So I can say 2 to the x equals 1 over 2 to the 10th to the power a half. So 2 to the x will equal 2 to the negative 10 to the power a half. And when I multiply the exponents on the right, negative 10 times a half is negative 5. Now we've got both sides expressed as a single power with the same base, so the exponents will be equal as well. And the answer is negative 5. Question F, we have log base 7 of 49 to the power negative 5. We want to know what that equals, so let's let it equal x. Right? When you convert from logarithmic to exponential, it will be 7 to the x equals 49 to the negative 5. The argument is 49 to the negative 5. That's what's been taken the log of. So that becomes what is written on the right side when we convert from logarithmic to exponential. We can express both with a base of 7. 49 is 7 squared. And power 2 to the power negative 5. You multiply the exponents and get negative 10. Bases are equal, so the exponents are equal as well. Now, you can use your calculator to check all of these. I'm not going to check them all, but like if you look at question F, if you want to know what that equals, either you use the change of base identity, or if you have this newer operating system, you can do it right in there. Log base 7 of 49 to the power negative 5 equals negative 10. That's what we got. You could do the same thing with the change of base identity. It would be the log of 49 to the power negative 5. Close the bracket after that, and that's divided by log 7. Using the change of base identity, it would look like that. Same answer. So as long as you have a log key on your calculator, you can check it. So now you have that change of base identity is something that you can use. Right? It's one tool that you can use to find the log of any number to any base. Remember, the only restriction is that you cannot take the log of a negative number. But now we see, because the change of base identity can be used, the base can't be negative either. Because if you use the change of base identity and the base is negative, you're going to be taking the log of a negative number on the bottom, which will not work. You'll get an error. Okay, so let's switch gears and talk about some transformations of logarithmic functions. It's the same principles as when we transformed all of our other functions. So we go from y equals f at x to y equals af b bracket x minus h plus k. Same principles as we've been doing all along. It doesn't matter what the original function is. So for this first question, this would be a transformation of y equals log base 3 of x. Okay, so our base graph here would be y equals log base 3 of x. So we need to know what that graph looks like. Okay? We need to know what that graph looks like. So if we start with y equals log base 3 of x, now we could do a table of values if we wanted to, using either the change of base identity or if you have the log function on your calculator. But the other option would be to write this in exponential form. It'll be 3 to the power y equals x. That's the same equation, just in a different form. And then what you might do is take the inverse of this. The inverse would be y equals 3 to the power x. Remember, a log is the inverse of an exponential function. An exponential function is the inverse of a log. So by writing it as an exponential first, and then taking the inverse, we can use a table of values to get points on the inverse and then just switch them around to get points on the original. For example, when x is negative 2, 3 to the negative 2 is 1 over 3 squared, or 1/9. When x is negative 1, 3 to the negative 1 is 1 over 3 to the 1, or 1/3. When x is 0, anything to the power 0 is 1. When x is 1, you'll get 3. When x is 2, you'll get 9. So these are points on the inverse of the logarithmic function. So now, for the actual logarithmic function, y equals log base 3 of x, our points can be found from the previous table of values, just switching them around. So this will give us points on the logarithmic function. 1/9 comma negative 2 is almost on the y-axis. Can you help? Okay, yeah, I'll be over in a second. 1/3 comma negative 1, 1 comma 0, 3 comma 1, and 9 comma 2. Remember that these logarithmic functions have a vertical asymptote, which is the y-axis. This is another reason why you cannot take the log of a negative number, because x must be greater than 0. The y-axis is an asymptote. So there's that graph. See if you can finish off those questions. Equations of the asymptote, domain, range, y-intercept, x-intercept, and mapping notation. Whoops, I'm sorry. That's the base graph. Now we have to do our new graph defined by this equation. And so if we do that, the x is replaced with an x plus 9, so that would be an h value of negative 9, which means the graph is going to shift 9 left. And then you've also got a k value of positive 2, which means the graph will shift 2 up. So everything is going to go 9 to the left and 2 up. When the vertical asymptote goes 9 to the left, it's going to change, obviously. It'll be at y equals positive 9. I'm sorry, I did that to the right. It should be to the left. So it's going to be at negative 9. And we can transform all the other points 2 up and 9 left. So the x-intercept was at 1, 0. It's going to go up 2 and 9 left. The point 3, 1 will go up 2 and 9 left. The point 9, 2 will go be up 2 and 9 left. So by doing the transformations, we actually got the y-intercept of the new graph. So now finish off those questions above. So the asymptote is now at x equals -9. So for part B, 1, a new asymptote, remember it's an equation, so it's got to have a variable and an equal sign. The second part asks for the domain and the range. So our domain will go from -9, which is not included, up to +infinity, which is also never included. Our range will go from -infinity to +infinity, right? The graph goes up and down forever. Part 3, the y-intercept, we got it by transforming the point 9, 2, because it went up 2 and to the left 9. That's where it crossed the y-axis. But if you don't know exactly where it is, you can always find the y-intercept by letting x equal 0. But again, we got it by transforming that point, the point 0, 9. I'm sorry, 0, 4. I apologize. 0, 4. And our x-intercept, while there is an x-intercept, it looks like it's between -9 and -8, and we can find it by letting y equal 0. If we take the equation of that logarithmic function and let y equal 0, it'll be log base 3 of x plus 9 plus 2. So you would subtract the 2 from both sides. And to solve for x, we would convert from logarithmic to exponential. Start with the base and cycle through. So that'll give us 3 to the -2 equals x plus 9. 3 to the -2 is 1 over 3 squared, or 1/9, equals x plus 9. So we'll subtract the 9 from both sides, which will be 81 over 9. So we have a common denominator there. And so x will equal -80 over 9. Again, it's between -8 and -9, like our graph showed, but closer to -9. Right, that's -8 and 8 over 9. Okay, so there's that one done. So this one will be a transformation of y equals log of x, log base 10 of x. I guess I did forget to do the mapping notation for this last one, so let's go back and do that. So part B is our mapping notation. Again, we went 9 to the left. So you subtract 9 from all the x values and then up 2. So you'll add 2 to all the y values. There's the mapping notation. So don't forget about that format. The last few diploma exams, there's been questions on there where you have to do a mapping. The nice thing about it is when they want to see a certain notation, like a mapping notation, there's usually a question, say in the multiple choice, that has the correct notation there as part of the question. So if you're not sure about something like that, often it's covered in the first section of the exam. Okay, so we need to see what the graph of y equals the log of x looks like. So like we did before, if we want to graph y equals the log of x, right, that's a common log, which means it's base 10. If you write that in exponential format, it's 10 to the y equals x. And you know, we did the inverse on the last one, but we don't really have to. You can write a table of values for this just by starting with values of y instead of starting with values of x. Nothing wrong with that. You can let y equal -2. And then x will be 10 to the -2, or 1 over 10 squared, or 1 over 100. You can let y equal -1. And 10 to the -1 is 1 over 10. You can let y equal 0. 10 to the 0 is 1. You can let y equal 1. 10 to the 1 is 10, and so on. So I've got the point 1/100, comma, -2, almost 0, 1/10, comma, -1, 1, comma, 0, and 10, comma, 1. Again, you've got a vertical asymptote here, which is the y-axis. So this is our graph. Okay, so you don't have to do that other step if you don't want to, of taking the inverse of the exponential function that we have written there, graphing that, or using a table of values for that to get the table of values for the new one. You could do it the way we just did it. Saves a bit of time. And so now we want to transform that to y equals log of x take away 10 minus 1. So we've got an h value of +10, which means the graph is going to shift 10 right. And we have a k value of -1, which means it's going to shift 1 down. So everything is going to go 10 to the right, including the vertical asymptote. And all the points will go 10 to the right and 1 down. So the x-intercept was at 1, 0. That'll go 10 to the right to 11, 0, and then 1 down. The point 10, 1 will go 10 to the right to 20. approximately right there, and then 1 unit down. So again, that will actually be the new x-intercept. Right, the point 10, 1 went 10 to the right to 20, 1, and then 1 down to 20, 0. That is the new x-intercept. So now if we answer all these questions in part B, we first want to state the equation of the asymptote, which will be the line x equals 10. Part 2 is the domain and range. The domain will go from 10 up to positive infinity. Neither are included. The range will go from negative infinity to positive infinity. The y-intercept, we can find that. Well, it doesn't look like there is a y-intercept, but if you let x equal 0 in that equation, you'd be taking the log of negative 10, which you cannot take the log of a negative number. So that's why there is no y-intercept. There is no y-intercept. And the x-intercept, we know that it is at the point 20, 0. You could also find it by letting y equals 0 in the equation and solving for x. Okay? The mapping. So we went 10 to the right and 1 down, which means you added 10 to the x's and subtracted 1 from the y's. So there's our mapping notation. Okay? All right. This one is a transformation of y equals log base 2 of x. But we're also going to have to do a bit of work, because remember, to find your h value, b and x minus h must be separated by brackets, and in this case they're not. You must take out a common factor of 2 to get the true h value. The b and the x minus h must be separated by brackets. So again, this is a transformation of log base 2 of x. So if I start with log base 2 of x, y equals that. The exponential format of that will be 2 to the y equals x. Start with the base and cycle through. So I'm going to use this to get a table of values so I can get my base graph. Again, because it's x equals 2 to the power y, I'm going to start with y values. When y is negative 2, x will be 2 to the negative 2, or 1 over 2 squared, or 1/4. When y is negative 1, x will be 2 to the negative 1, or 1 over 2 to the positive 1. When y is 0, anything to the power 0 is 1. When y is 1, 2 to the 1 is 2. When y is 2, 2 squared is 4. So I've got the point 1/4 comma negative 2, 1/2 comma negative 1, 1 comma 0, 2 comma 1, and 4 comma 2. Again, the y-axis is an asymptote. So there's the original graph, the base graph. Now, for our new one, is y equals negative log base 2 of 2 bracket x plus 3. The fact that a is negative means that we're going to have a reflection about the x-axis. A is negative 1, so there is a reflection about the x-axis. The fact that we have a b value of 2 means that there's a horizontal stretch. And you must say what axis it's stretched about. So it's a horizontal stretch about the y-axis. And remember, the scale factor is always the reciprocal of b. So the horizontal stretch factor about the y-axis will be by a factor of 1/2. You must say about what axis the stretch is about. And then we have an h value of negative 3, which means the graph is going to shift 3 left. So remember how we did these before. We took our original points and we did these transformations. Okay, we do know, because it goes left 3 units, that the vertical asymptote will go left 3 units. It'll be at negative 3. Okay, a couple points that I have on here. And maybe it's helpful to do our mapping notation right now. So if we do part V right now, the ones that will affect the x's are your b parameter and your h parameter. You're going to multiply all the x's by 1/2 or divide them by 2, and then you're going to subtract 3. The y values are just multiplied by negative 1. So I don't have to use all the points that I have here. I can start with the point 1/2 comma negative 1. I'll multiply the x value by 1/2, which will give us 1/4. And then I will subtract 3. So 1/4 take away 3 would be 1/4 take away 12 quarters. That's 3. That's negative 11 quarters. And the y value is multiplied by negative 1, so that'll become positive 1. So the point 1 comma 0 you'll take half of the x value, so half of 1 is 1/2. Take away 3 is like taking away 6/2. That's negative 5/2. And when you multiply the y value by negative 1, in this case it doesn't change because it's 0. The next point is the point 2 comma 1. Take half of x, half of 2 is 1, take away 3 is negative 2, and the y is multiplied by negative 1. Our last point is the point 4 comma 2. Take half of the x value, half of 4 is 2, subtract 3 would be negative 1, and the y value is multiplied by negative 1. Okay, so there's the points we'll put on our new graph. First one is negative 11 quarters, which is negative 2 3/4, comma 1. Negative 2 3/4, comma 1, approximately right there. The next one is negative 2.5, comma 0. Right there. Then we have negative 2, comma negative 1. And negative 1, comma negative 2. This one goes downwards instead of upwards because of the reflection over the x-axis. So there's our new graph. The asymptote would be at x equals -3. The domain will be from -3 to positive infinity. Again, rounded brackets being used there. The range goes from -infinity to positive infinity. This one will have both a y and an x-intercept. Our y-intercept, remember, is always where x equals 0. So if we take the equation and let x equal 0, it'll look like that. So it's negative log base 2 of 6. Inside the brackets, you have a 0 plus 3. That's then multiplied by 2. And we can use our calculator to get that. Whether you use the change of base identity or if you have a new operating system. Log base 2 of 6. And I forgot to put the negative in there first. There we go. It's negative 2.58 approximately. So our x-intercept is the point 0, that's our x-intercept. It's negative 2.58, 0. Sorry, that was our y-intercept. I had it right the first time. And our x-intercept is where y equals 0. So it'll be where 0 equals negative log base 2 of 2 bracket x plus 3. So we need to solve for x here, and you can divide both sides by -1 and it won't change the left side. And now we will convert from logarithmic to exponential by starting with the base and cycling through. 2 to the 0 is 1. Divide by 2 and you'll get a half, or 0.5 equals x plus 3. And 0.5 take away 3 will be negative 2.5. So there's our x-intercept, negative 2.5, 0. Okay? So this last one. Again, to get our true h value, b and x minus h must be separated by brackets. There's a common factor of -1 you would take out. And so there's the equation that we need to work with. And this will be a transformation of y equals log base 3 of x. In exponential, that'll be 3 to the power y equals x. And we can use this to generate our table of values. Once again, starting with y values. 3 to the negative 2 will be 1 over 3 squared, or 1/9. 3 to the negative 1 will be 1 over 3. 3 to the 0 is 1. 3 to the 1 is 3. And 3 squared is 9. So this gives us points for our base graph. The base graph has a vertical asymptote at x equals 0, the y-axis, and then it goes through these points. So there's our base graph. And now we have to get our points for our transform function. 2 times log base 3. Again, it's negative 1 bracket x minus 1. So the first thing we see is we have an a value of 2. So that's going to cause a vertical stretch about the x-axis. By a scale factor of 2, because that's what our a value is. We have a b value of negative 1. That's going to cause a reflection about the y-axis. And we have an h value of positive 1, which is going to cause the graph to shift 1 unit to the right. So from this, we can write our mapping notation. The part that's going to affect the x values is the reflection over the y-axis. You'll multiply x by negative 1. And then if we go 1 unit to the right, we're also going to add 1 onto all the x values. The y values are multiplied by 2 because of our a value of 2, our vertical stretch about the x-axis by 2. So again, we don't have to use all the points here, but we'll use some of them. Because the graph shifted 1 to the right, that means our vertical asymptote will shift 1 to the right. And I'll start with the point 1/3 comma negative 1. So our x of 1/3 is multiplied by negative 1. They become negative 1/3. Plus 1 would be 2/3. And the y value is multiplied by 2. So there's the new point. 1 comma 0. You're going to multiply the x value by negative 1. It'll become negative 1. Plus 0 is 0. And when you multiply the y value of 0 by 0, it stays 0. The next point is 3 comma 1. So multiply the x value by negative 1, will become negative 3. Plus 1 is negative 2. Our y value is multiplied by 2, so 1 times 2 is 2. And the last point is 9 comma 2. So the x value is multiplied by negative 1, will become negative 9. Plus 1 is negative 8. The y value is multiplied by 2, it will become 4. So there's our new points. 2/3 comma negative 2. So that's approximately right there. 0 comma 0. This graph will go through the origin. That's both our x and our y axes then. Negative 2 comma 2. And negative 8 comma 4. So there's our new graph. Part 1, the equation of the asymptote will again be x equals 1. Part 2, our domain. That'll go from negative infinity to positive 1. Our range will go from negative to positive infinity. And as we've said, both the y and the x-intercepts are the point 0, comma 0. X and y intercept at 0, comma 0. Okay? So what you can work on is page 389, questions 1 through 4. And next week we should be able to go through your chapter 7 quiz. I will post the solutions to these on Google Classroom Notes so you can check your answers, okay? Yeah. Did everyone get that page?